Hello, my name is Robel Lemma, presenting the final Capstone project for Data 670. The focus is on predicting US flight cancellation from 2019 to 2024 using integrated aviation data and machine learning. So this project explores how predictive analytics can enhance operational insights, particularly during the period of disruptions like the COVID-19 pandemic and beyond. This presentation begins with the project overview and the data sources, followed by data preparation and feature engineering. Next are Tableau visuals, key predictive features, model comparisons, and the champion model justification. The later slides cover KPI results, recommendations, limitations, and future work. The lesson wraps up with reflections, a summary of the next steps, references, and time of questions. To begin, the central challenge explored in this capstone is the prediction of US domestic flight cancellations, an issue with significant consequences for airline reliability, operational stability, and passenger satisfaction. The objective was to develop interpretable and accurate models by leveraging both BTS performance records and FAA safety reports. The scope focused on using aviation data, predictive modeling to guide proactive interventions during disruptions. Four key performance indicators framed the analysis: achieving high ROC AUC for classification strengths, maintaining F1 score, fairness, ensuring SHAP-based interpretability, and capturing structure shifts such as those caused by COVID-19. So these KPIs shaped both feature design and model selection. To support these objectives, data from the two distinct sources was combined. Over 7.6 million of flight records were sourced from the BTS on-time performance datasets, covering the 5 strategic quarters. To complement this, more than 23,000 FAA incident reports were filtered and integrated to provide safety context. The selected quarters span pre-pandemic condition in 2019, peak operational disruptions in 2020, and recovery periods across the 2023 and 2024. Because the datasets lacked direct join keys, they were merged by quarter using a derived time level, enabling trend alignment between safety events and operational outcomes. To ensure high-quality analysis, the data underwent several preparations and cleaning steps. This funnel represents the end-to-end pipeline, starting with raw data loading, followed by cleaning, encoding, balancing, and finally modeling. The initial cleaning removed missing values and standardized time formats, including binning departure times, parsing flight dates. Records were filtered to focus only on domestic flights. So due to low cancellation rates, just 3.3%, the dataset was imbalanced. So SMOT was used to synthetically balance the classes. To improve model training speed, downsampling techniques were applied to the full datasets of over 7 million records. With a clean foundation in place, the next step involved deriving features that would improve model signals. Feature engineering emphasized both flight delays, behavior, and safety context. A log transformation was applied to departure delay to handle extreme values. Time of day was grouped into bins: morning, afternoon, evening, and night to highlight the temporal patterns. From the FAA datasets, an incident rate per 1,000 flights was calculated to quantify local safety risks. So these new features played a central role in model learning, were later validated using a SHAP interpretation. So to prepare for modeling, key categorical fields such as carrier, day of the week, origin, and quarter were encoded using one-hot techniques. To visualize early trends, the analysis shifted to Tableau for explanatory insights. So this chart shows the percentage of US domestic flight cancellations across the 5 selected quarters from pre-pandemic to post-pandemic recovery. As clearly seen here, Q2 of 2020 shows a dramatic spike with over 56% of the flights cancelled, reflecting the height of the COVID-19 disruptions. In contrast, Q1 of 2019, a baseline pre-COVID period, had a significantly lower cancellation rates of around 17.7%. So the trend following the pandemic shows a gradual return to stability. Q3 of 2023 and Q4 of 2023 shows moderate reductions, and by Q1 of 2024, cancellation rates declined further to just over 11%. So this pattern confirms a strong structural shocks during the pandemic, followed by a steady operational recovery in the US airline system. Now, turning to the features that consistently surfaced across all models, the top 5 predictors were shared regardless of algorithms, a strong indicator of signal strength. Afternoon departures, longer delays, and high incident rates stood out as especially influential. So notably, the inclusion of the 2020 quarter to quarter level helped the models capture the unique disruption caused by the pandemic and recoveries that followed. So these features were not chosen randomly. Domain logic guided the design, and the sharp validation confirmed their impact on predictions. Ultimately, the selected features not only made the model smarter, but also made their decisions easier to explain. A key win for stakeholders' trust. Now, this model comparison summarizes the 5 models: logistic regression, random forest, light GBM, support vector machine, and naive Bayes. Performance was evaluated using accuracy, precision, recall, F1 score, and ROC AUC. Among them, light GBM achieved the highest score across all the key metrics, with a ROC AUC of 0.9559. It demonstrated strong classification capability and reliable balance between the detecting cancellations and avoiding false alarms. So random forest also performed well, but light GBM showed more consistent results across classes, particularly for rare cancellations. Visualizing these results side by side highlights why light GBM was selected as the top performer. Here, the ROC curve used to assess how well each model distinguishes between cancelled and non-cancelled flights. So the curve plots the true positive rates against the false positive rates across the different thresholds. So a model with a perfect score would curve up to the top left corner. So light GBM shows the strongest curve with an AUC of 0.9559, indicating a very high ability to correctly classify both cancelled and non-cancelled flights. Random forest follows closely behind, while naive Bayes trails lower on the curve. What's important here is not just the AUC. It's also how each model handles the trade-off between the missed cancellation and the false alarms. Light GBM struck the best balance, minimizing false negatives, which are especially costly in airline operations. So the sharp plots further clarify why light GBM performed well. Features like departure time being, especially afternoon departures and a log transform departure delays, had the largest impact on prediction outcomes. So these insights align with operational experience, validating the model's learning process. So these results support the final selection of a champion model. Among the models evaluated, light GBM stood out as the top performer. It delivered the highest AUC at 0.9559, along with strong recall of 0.92 and an F1 score of 0.89. Beyond raw metrics, interpretability played a major role in model selection. Sharp explainability tools were used to uncover how individual flight features contributed to each prediction. The chart waterfall plots shown here illustrate the cancellation risk for a single flight. Starting from the base value, each bar shows how features like departure delay, time of a day, or incident rate pushes the model toward prediction of a cancellation or not. This level of transparency helps stakeholders understand not just what the model predicts, but why. It builds trust and supports smarter operational responses. To further validate model alignment with trends, Tableau was used to visualize delay patterns. Here, this stacked bar chart presents the flight by time being and quarter. So each quarter's bar is divided by color-coded time beings: morning orange, afternoon blue, evening red, and night teal. So a few key patterns emerged. In quarter 2 of 2020, afternoon flights experienced an unusual high number of delays, despite overall flight volume being lower. So during the post-pandemic quarters like Q3 and Q4 of 2023, morning delays becomes dominant again, suggesting a return to typically traffic patterns. By quarter 1 of 2024, departure delays were better distributed across the day, with improved balance between morning and afternoon periods. So these observations help identify when an operational congestion is most likely to occur, which is essential for both scheduling and resource planning. So this table summarizes model performance against the 4 key performance indicators. Each KPI was successfully met or exceeded. So the light GBM model delivered a high ROC AUC score above 0.95, ensuring strong predictive accuracy. It also provides sharp-based interpretability, enhancing trust in the model's prediction. Notably, the model demonstrates disruption sensitivity by capturing cancellation spikes during the COVID-19 lockdown in 2020 quarter 2 and recognizing recovery trends through 2024. In addition to meeting the defined KPIs, the model exhibits operational visibility. It trained efficiency on over 7.6 million records and supports potential real-time deployment, making it suitable for integration into airline decision support system. Based on these results, several deployment opportunities were considered. To move from the analysis to impact, the champion model is ready for integration into operational dashboards. So these dashboards should provide cancellation risk scores updated in real time to support proactive decision making by operation teams. Enhancing data inputs is also critical. Connecting live flight status, airport conditions, and weather APIs will improve the model responsiveness to fast changing conditions. Finally, exploring stacked ensemble methods may further boost performance. Combining multiple models can improve resilience across flight seasons and operational shifts. So every project has its limitations, and this one was no exception. So the several limitations shaped this phase of analysis. FA incident reports could not be linked directly to individual flights, limiting granularity. Weather data was not yet integrated, which reduced environmental precision. Future work should prioritize structured weather integration using sources like METAR reports or FA alerts can enhance disruption prediction during storms or visibility drops. Improved sampling and learning strategies such as SMOTS, ENN, post-sensitive learning, and ensemble stacking can refine class 1 detection, especially during high volume periods. Model deployment also requires further scaling. Interactive dashboards built with tools like Streamlit or Flask can allow real-time user engagement, retraining triggers, and seamlessly integration into airline systems. Beyond technical progress, this project also offers several professional takeaways. This project highlighted the power of ensemble methods. Light GBM outperformed all other models, even under a significant class imbalance. Compared to linear approaches, ensemble models were better at capturing complex flight cancellation patterns. Another important takeaway was the value of the model transparency. Sharp explanation did not just improve interpretability, they boosted stakeholders' confidence by clearly showing which features influenced prediction at a flight level. So feature engineering was critical. Variables like departure delay, time of a day beans, FA incident rates aligned well with real-world disruptions. In fact, the model accurately detected the COVID-19 impact through these learned and engineered signals. Additionally, integrating FA data, even at an aggregate level, provided context that made the model more sensitive to unusual events. Finally, by applying techniques like SMOT and downsampling, we maintained stronger performance while training efficiently on over 7 million rows. Let's now summarize the key takeaways and look ahead. These slides summarize the key findings and future direction of the project. Light GBM emerged as the best performing model, offering high AUC sharp based interpretability essential for building trust in high-stake environments. The integrated BTS and FA datasets enabled accurate flight cancellation prediction, generating insights that support operational planning and resource allocation. The current data pipeline is ready for dashboard deployment in live operational settings. The architecture is scalable for other domains such as cargo logistics and international operations. By aligning analytics with storytelling, this solution strengthens the link between the data science outputs and business decision making. And these are the references that used throughout the project. And this concludes the presentation. And thank you for your time and attention. Open to any questions or feedback.